Well, welcome everybody. Can Zoom hear me fine? Just a thumbs up. Okay, cool. Looks like we're all set. So today I'm going to be yapping about transformers. Clearly you all know that. Just a quick intro about me. Kind of wear two hats. One, I'm a research fellow at UD. I'm a PhD student in bioinformatics. This is sort of the things so I work in the Glycorn lab. We're just in a really broad variety of problems. I have this stuff up here just in case any of that stuff is interesting to you guys, and if you might want to chat about it after, or network or so forth. I'm just trying to get my whiteboard up here. Yeah, the other hat I wear is through a company I founded with a couple other people called Synthyra, which sort of tries to take the fundamental research behind the stuff in the Glycorn lab and it tries to commercialize it. But in both those hats, pretty much everything I do involves transformer neural networks. We have a couple TAs here today. I'll let them introduce themselves.
I'm Nico. I started my college journey at Delaware Tech here nearby, and then I got my bachelor's at UD. I did undergraduate research at the Gleckhorn lab during my last year, my senior year at UD, where I first learned about protein language models, and I sort of was very interested in that, so I decided to follow along that path for my graduate studies. And I'm currently a PhD student in the Bioinformatics and Data Science program. And yeah, in my research, I work with protein language models. We apply them to problems like enzyme discovery and design. And we, sort of try to enhance their predictive capabilities to help us elucidate biology even more than we currently can. And Logan will be talking about Protify later on, which is a platform where we make it easy to use, these protein language models and other chemical language models. So.
Yeah, sort of backwards talking away because we're going to tell you about how important everything is and then how you don't need to know any of it. So you can sort of standardize it. That's not true at all. It's good to know, but then we have Tamar here.
I'm Tamara. I'm an undergrad in the Applied Molecular Biology and Biotech program in the College of Health Sciences. And I also have a computer science minor in the Bioinformatics graduate certificate. I also work in the Glycorn lab with Logan. I was also an NIH summer intern 2 summers ago, and I do EMS and I am a teaching assistant on campus. And my research interests are kind of on the intersection of computational biology and medicine, focused on protein language models and their applications. So protein design, drug delivery, and patient care.
Thank you. Yeah, and we have most people on Zoom right now, and there's less people sort of in the room than I was anticipating, which is good. We can actually, if you don't mind, maybe we can go around and give name, just where you're working and what you do, because maybe during lunch everyone can network, and that's great. So let me start here.
Sure. I'm Barb Farrell. I work with several professors in the AP Bio building, Eric Womack, Sean Polson, and Jeff Furman. So collaboratively, we do primarily viral ecology work, looking at unknown virus populations in the environment and trying to figure out how they're impacting their microbial hosts and impacting ecosystems in terms of nutrient cycling and things like that. We're using protein language models much more because we focus on replication proteins and how those particular proteins are so central to genome replication, but also have these biochemical implications for how viruses do what they do, like how quickly they're replicating and how many viruses they're producing when they replicate. So we're using protein language models quite a bit to look at those particular proteins.
I can't imagine how viral replication would be, important for studying diseases or anything.
No implications whatsoever.
Yeah. Awesome, thank you.
Thank you.
Back here.
Oh, my name is Zaina. I'm also an applied molecular biology and biotechnology student. And I do research with the same people as Barb. And study viruses that carry DNA polymerase V, and I use protein language.
PLM users so far, that's awesome. Okay, Suhatra?
I'm Suhatra Varai. I am also a PhD student in bioinformatics data science. I do not work in viruses, so I work with Melinda Duncan, who works on cataract and other eye disease mechanisms. I don't particularly use like super machine learning techniques, but definitely transcriptomics and all those kind of data.
After today.
Yeah.
Maybe. Okay, Mike?
Hi, I'm Mike Healy. I'm a new MS bioinformatics data science student. My background's electrical engineering, software, and high-tech manufacturing. So I'm interested in the intersection between bioinformatics and biomanufacturing, perhaps. I've been studying some of these software techniques, software languages for a few years. I'm looking forward to the application of this area.
So, Vishnu, back. We're just doing a quick intro. What you do?
My name is Vishnu Chaudhary. I'm a new master's student in bioinformatics. My background is biology. I am interested in learning, especially the bioinformatics tools that are useful in analyzing the big data sets where the machine learning and artificial intelligence algorithms are used.
Awesome.
Hi, I'm Julie. I'm a PhD student in bioinformatics, and I work with Lucas Liu in the mechanical engineering department. So we mainly work with osteoarthritis and cartilage diseases. So we're trying to find therapeutics for that. Currently, we're doing a high throughput drug screen, but it's very wet lab, where we're collaborating with the lab right now for large language modeling and text mining. I'm kind of trying to hope to find some other machine learning that we could use for this project.
I'm sure it can wiggle its way in there. It sort of always can. Great, thank you for doing that. I think that's awesome, and I'm always trying to promote networking. Yay! Today, yeah, obviously we're learning about transformers, but we're not going to talk about Autobots, Decepticons. Unfortunately, those are very cool, but sort of the ones introduced in 2017. Of course, this is the seminal paper, "Attention is All You Need," where mostly Google Brain introduced some of the fundamental techniques, but these types of ideas had been around for a while, particularly different types of attention mechanisms, although they really get fleshed out here. And this is kind of where they apply scale and compute. Again, that's one thing industry loves to do, is throw compute at the problem, and they actually end up discovering some interesting things. Of course, this isn't the beginning of natural language processing even, but it is the start of the LLM revolution. But we're not going to be talking about a lot of the sort of introduced architecture that they have. They had this encoder decoder schema. Right now in the field, they're sort of removed from each other, and so we'll go back and forth talking about both. But starting from as basic as we can, we'll make them much easier to understand. So what I'm going to be talking about mostly is a lot of not notation, operations, different basic linear algebra, and then some basic neural network stuff. And then we'll get into some basics of LLMs and some practical tips and tricks. And then I just want to let it be a Q&A, just go back and forth, see what we want to talk about. And beyond that, there's some workbooks, some notebooks, Python notebooks that should be interactive and helpful to illustrate some of the concepts. What I'm not going to talk about is algorithms and different optimization schemes, mostly because I don't think you really want to hear me talk about that. I wouldn't do a good job. So I want to give some intuition behind things like gradient descent, but I'm not going to sort of dictate every detail. Hopefully that sounds okay. I want to start with sort of the most fundamental unit of machine learning, really, which is the vectors. Of course, vectors introduced in normal physics textbooks or mathematics classes. It's all sort of the same concept, which is there's this arrow pointing somewhere, right? So instead of just having a single scalar number, we're combining different numbers, and that sort of lends itself to this geometric interpretation, or you can plot them with, again, a magnitude and direction. Of course, you can do vector arithmetic. You can add them, subtract them, multiply them. Those are what's called linear operations. And again, you can sort of have any size vector you'd like. So down in this image on the bottom, see a 4D vector, that has 4 numbers. D, of course, refers to dimensions, and that's the number of sort of orthogonal axes instead of just X, Y, Z. If you have 4 dimensions, you need some other U there, I guess, and that sort of stacks up. But typically when someone says dimension, they just refer to how large a vector is. Notation is kind of varied. You might see it with an arrow at the top. Oftentimes the shorthand is you just have a lowercase letter instead of uppercase letter for a matrix. Of course, the next concept is matrices, which I guess is just a vector of vectors, but in reality it's even simpler. There's a 2D array of numbers. Matrices are really convenient to model lots of types of data. Of course, vectors are too. Oftentimes they're sort of talked about in the linear algebra space from either a column or row perspective, where you're either messing with a row-wise or column-wise operation. One of the neat things about matrices is their multiplication property is sort of not commutative. So actually the direction of matrix multiplication matters a lot, and we'll get into how that actually can be used in machine learning. Of course, there's some fundamental concepts on the right here. By the way, if you want to figure out what blogs or resources are behind the images, I just added links to them. So when I send out the slides, if you want to go through them, then you just click on them and it will take you to where they go. So of course we have the identity matrix. It's a fundamental concept here. By the way, please stop if any questions, but I think you can sort of draw on this. Yeah, identity matrix, of course, just ones down the diagonal and zeros. It's called the identity because if you multiply something by the identity, you get itself. We'll talk about, again, map moles a bit. Let's go to the next slide. Oftentimes they're introduced in this form of sort of linear equations where you have n unknowns and n equations, and you try to sort of solve for x, y, and z in this case. That's not really the sort of interpretation we often associate with machine learning, although I guess in some ways it's equivalent. But I just wanted to touch on this. I'm sure it perhaps has been a while since any of us did the actual elimination process to solve this. But there are, again, sets of rules to do stuff like this. And then I just want to touch on tensors. Tensors is a word that's thrown around a lot in machine learning. But really it just refers to any array of numbers that has more than, I guess you might call 2 dimensions, but I prefer to use the nomenclature axes. So basically, if we wanted to write out a vector, we might say it is a, so let's do a column vector first. And so we have like ABC. And so we always write out matrices vectors. I guess, of course, a vector is just a 1D matrix, but rows by columns is the important thing. No. So in this case, we have how many rows?
3.
1 column. We write 3 by 1. Have some more elaborate matrix. Maybe there's zeros everywhere else. Maybe this is a 3 by 3, so we call it 3 by 3. But a tensor might have another axis here where we're actually stacking together multiple matrices into one object. And in that case, you'd add another axis here or here. Sort of depends on how you arrange it. One really important application of a proper tensor, in this case, a 3-axis tensor, so something by A, B, C, in terms of what the dimension sizes are, is like an image. of course, you'll see that height times width times the channels. So that's height and width is obviously the size of the basic image, and C for grayscale image. So that's just like one channel. It's colored from black to white. Usually 0 to 255 in there. Color images, of course, have 3 channels, so red, green, blue. So that's a one really key sort of where a tensor can come into play. In Python, PyTorch, sort of everything is referred to as a tensor, no matter what size it is, which is just an important distinction. It doesn't mean that the tensor object is sort of sufficiently large or anything. It's just that the class tensor in Python comes with a lot of sort of inherited properties that make it useful to do things like machine learning. So that's what tensors are. This context, of course, tensors also mean a bunch of other things in physics, but they're sort of not related. Well, I'm sure they're related, but another thing I want to go over before like getting into nitty-gritty is this MNIST data set. I use this a lot as like an example data set and sort of just go over what's in there is that there's 60,000 images and they're all grayscale. So technically you'd call them height by width by 1, but that's really equivalent to height by width as well. You can reshape that in different ways within Python and PyTorch. The size of the data set is 60,000 images for training, 10,000 for testing. Evaluation splits are really important. I'll touch on that a bit later. But there are 10 classes for the 10 digits. And if we zoomed in on each one, we'd really just see like a matrix with a bunch of numbers in it. Again, 28 by 28. So you can also flatten that into a single vector. So you just stack the 28 things end to end. That happens to be 784. So whenever someone's talking about dealing with MNIST data, it's either in the form of 20 by 28, at least for this data set, and or 784 vector. So the first sort of very fundamental concept is one type of vector operation that doesn't actually result in another vector, it results in a number. And that number is actually a really important measurement for machine learning in a way. So dot product is a very simple operation. If you have sort of 2 vectors, let's say 1, 2, 3, 4, 5, 6, our favorite iPad password there. The dot product between A and B, A dot B, is going to be sort of this element-wise multiplication and then added together. And what I mean by that is going to be like 1 times 4 plus 2 times 5 plus 3 times 6. I guess that's going to be 4 plus 10 plus 18. And what is that? 32. So there we got a scalar out of 2 vectors. What does that tell us really? Well, unfortunately, not a whole lot without additional context. One thing we can make equivalent to a dot product is actually sort of the magnitude of the vectors. That's how long it is, multiplied by cosine of its angle. And so in there is some sort of geometric measurement of what angle this vector is at. Of course,
That's
Video.
Yeah.
oh, geez,
swing it to the other side.
great point. Yeah, I can just get rid of that. Right? Thank you. And then of course, so you can sort of cosine, if you divide by A and B. By the way, what's one way you could calculate the magnitude? A or B? Anyone remember? I mean, I guess one way you could just do the distance formula between these points and 0. If you go through that, it's just going to be sort of every element minus 0 squared. So it's sort of like a squared sum, and then you can take the square root. That's going to be the magnitude. So you can calculate that directly from the vector, which is good. And because you can always have that and the dot product, if you have two vectors, you can sort of always have enough information to figure out the angle between them, or at least more directly the cosine of the angle between them. And so this is a very important vector heuristic. And in some way, dot product in itself is a really good vector heuristic because it sort of has all that baked in there. What that means is the intuition here is like a really high dot product implies a high amount of similarity between the two vectors. And while that doesn't hold all, everywhere because it's scaled by the magnitudes, it is a good like one-off shot to compare two vectors and be like, those are actually quite similar. If you actually need a normalized value, you need to normalize the first, so divide by the magnitude, and you get this sort of cosine relationship. Of course, you could also find the Euclidean distance, or the basic distance formula between two vectors, and that's another measurement. I think I maybe even have that here, right? So different types of vector similarity heuristics. So again, dot product, pretty good, but not that good because sort of unscaled. Cosine similarity, if we remember, cosine sort of ranges from -1 to 1, starts at 1. So if two vectors are at the same angle with respect to the origin, it will have a cosine similarity of 1 because they are, the angle between them is 0 and the value of cosine at 0 is 1. The most dissimilar they can be, arguably the most dissimilar they can be is orthogonal. That'd be cosine of 0. And that brings up a good point. The dot product of two vectors is 0, precisely because of this fact. So in most applications, this is the most dissimilar vector. You might say the opposite vector is more dissimilar, but that's sort of kind of perfectly inversely correlated, right? So in most applications, that's actually in some ways equivalent to cosine of similarity of 1. But as you get to higher dimensions, that sort of means more to be opposite. But in general, orthogonal is the most dissimilar you can be. And then, of course, there's other types of distances. The most common we see is the L2 distance. There's a formula for the L distances. I guess I can draw it out. So if we think about distance formula, we have like x1 minus x2 squared, and we take a square root of that. We call this L2 because the root is the second root and we square it. So the Manhattan distance is actually L1 distance, which is just sort of the direct subtraction. And of course you have L3, but that isn't really used a lot. Just wanted to point out that there's a pattern there. Okay, and so far, questions, comments? Cool. Dot products are very important. Precisely because of mammals. So matrix multiplication really just an array of dot products. The formula sort of highlighted on this bottom, which maybe is hard to follow, but you're essentially dealing with the rows of one matrix against the columns of another. And if you call this A and B as vectors, you take their dot product, and that shows up in so this is the ith row, the jth column. That would show up in the jth index of the matrix. Is everyone familiar with matrix indexing? Just like we write matrices row by column, you can index them row column and sort of find what is there. In this case, our matrices are what shape on this bottom? The first one, maybe we'll call this matrix A and B, this result C. What size is A?
2 by 3.
Yeah. Perfect. if they're all real numbers, you'll typically see it written like this, 2 by 3. Of course, you could have other types of numbers. Maybe you've exclusively integers, but in machine learning, we often have real numbers. B, of course, if you can multiply it, it has to have the same amount of columns as this one does. Sorry, rows as this one does columns. So this one must be a 3. It's actually a 3 by 2. There's a neat trick to figure out what the resultant matrix is going to be if you write out the shapes. Sort of do this little cancel. It's going to be 2 by 2. And again, we see that we have a 2 by 2 and we actually have 4 dot products. So that's the most basic description of matmoles. They're really, really versatile operations. I wanted to highlight that there are things these called permutation matrices. The most simple one is, of course, the identity, which is nothing to the matrix. So if we have IA, it's going to get A. But if we switched around the elements in I, for instance, we put a 1 here and 1 here. So we just sort of switched the 2 rows. I want to point out that this is something pretty unique to some matrix here. Does anyone have a guess? Basically, I mean, we could just go through the matmole, right? So if we look at this, 0, 1, 0 versus this, dot product of that is just 4. That is going to go here. And I'm doing this right. Let's see. Basically, it's just going to switch the order of the, in this case, I believe this is going to be the rows. Yeah. So it's just going to be 4, 5, 6. This one's going to move up here, move down here. So we switched the rows in our identity matrix. We end up switching the rows over here. So we do a very simple permutation. And this is important because this basically allows you to index matrices and reshape matrices through matmoles. So if you design a matrix of 0s and 1s the right way, you can end up pulling out 1 column or 1 row of a matrix or even 1 index. And when we sort of get into what's important for machine learning later, everything has to be differentiable so that gradient descent can sort of work its magic. And so matmoles serve as the differentiable way so that we can do these types of important operations. So when you're in PyTorch and you index something, well, I mean, on the back end, it's just a matmole, so that's differentiable and et cetera. At least that's the way I understand it. Maybe it's optimized in some other fashion, but differentiability is very, very important. Let's see. One other sort of intuition you might glean is because it's an array of dot products, the resultant matrix is sort of a prescribed similarity measurement of A and B. So if you have A, B, C, of course, we had a row 1 by column 1 times column 2 by row 2. Maybe in this case, well, it's going to be still row by column. My bad. It's just that column 1 and row 2 must be equal. So basically, what I'm trying to say is for the ith row of A and the jth column of B, that will show up in the ith jth position of C, and it is a dot product. So it's actually saying like how similar in a way the rows of this matrix are to the columns of this one. which is sort of an important intuition for trying to prescribe some meaning on how like the black boxes work. Of course, if you normalize the matrices first and then you do the map mol, it wouldn't actually be a dot product matrix, it'd be a cosine similarity matrix. And then you literally have the angles in between the rows and columns just by doing this multiplication, which is sort of very useful. So I just wanted to touch on derivatives. I'm not going to obviously talk about a lot of calculus. Besides, it's not something you sort of directly use. It's sort of always on the back end of things like PyTorch, which is great because it can be sort of complicated. But again, derivatives are just it's a one function that's a rate of change of another function, at least instantaneously. And of course, you can take the derivative of matrices and vectors. One helpful interpretation of that is to look at them like that linear system of equations that I mentioned before. And so you can just sort of, you would either do a full or partial derivative at each step or each element, you end up with your derivative. But what's important is that not every function is differentiable. We have some examples on the bottom here of different breaks or kinks or infinitely, there's a vertical tangent thing. Those break our machine learning algorithms. It will not work. The whole chain, everything between the input of your data and the output of the answer has to be differentiable. Otherwise, you can't train it through gradient descent. And so one thing I wanted to go over is sort of the simplest machine learning process, perhaps, which is something I'm sure everyone is familiar with, called linear regression. If we form some data matrix, X, we'll see that we have one large matrix at n by p. In this case, it's actually p different observations of an n-length variable. So this x1 is p, and each x is corresponding to a y. So it's almost like we have some observation x, and we want to predict y1 from this. But instead of just having all of those written out in some lists, we can shove them together. And so this x is really a whole data set, not just one data point. And the y is also the whole data set, except it's the output, it's the targets, it's the objective. And the objective is to find some function which takes in some x and gives you the y. Equivalent to solving this formulation on the bottom, which is if we find some parameters b, beta, which is again going to be a vector of length p, we can apply that to each x variable and get an answer y through a memo. So y, of course, is r by 1. X is going to be n by p, and beta is going to be what size if x is n by p. Let's got to start with p because it's got to be an appropriate memo, p by 1 in this case. And sort of equivalent to this argument formulation. Argument just means we're going to minimize that, which is essentially saying this is the predicted y pred, maybe call it y hat, minus the real y. So we're going to minimize the error here, or at least the mean squared error, which is a very common heuristic. So if we minimize that, minimize the error, perhaps we've found the best parameters beta that approximate this task. It turns out it's not the best beta, but it's a good one. We'll get into that in just a second. But here's a more concrete example of CAR's data set. So there's n of 805, so there's 805 examples here, with each sort of x variable being 11 observations about a car. Some of them are numeric, like the mileage, that's easy. Others are also numeric, like how many cylinders it has, etc. Some of them are a bit more complicated. They're categorical variables. So they're not some float or integer. This is, again, one example here is the make of the car. There's only so many car makes, and so, however many are in this data set or how many categories you have, One way to featureize this is to map each one to a unique integer. That's one way to do it. So, Buick could be 0 and Chevy could be 1, etc. You could do this for model and the trim. There are better ways to featureize this that we can talk about in a second, or at least sometimes better. But mapping to an integer is a perfectly reasonable modeling approach. And in that case, we would again still have p equals 11, and we could try to solve this linear model. Again, the sort of objective, oh yeah, I forgot to mention the price is y. So that's what we're trying to predict. So put in everything about a car, spell out the price. That's very useful, right? Because the dealership can train a model on a maybe even a larger data set. If they have a low error, then they have a really good way to estimate the actual value of the car. Maybe they can bump it up, right? So in the case, price times 1 beta times mileage. That makes sense. Cool. So it turns out linear regression has a closed form solution, at least for one of its solutions. This LS beta sort of refers to linear unbiased estimator. So bias and variance are sort of really important concepts in this space. These equations here that solve it are called the normal equations. And what's nice about linear regression is it has a closed form solution as long as you can take the inverse of this x transpose x. Because I forgot to mention that the inverse of a matrix is just a matrix that gives you the identity. Something like this. And transpose, you just flip it along the diagonal. So you had 1, 2, 3, 4. Oh, let's just keep going. 9, 1, sure. Flip it along this central diagonal. It's going to end up 1, 2, 3. And then this can be 5, 8, 6, 1, 9, 1, and so on. It actually flips the rows into columns. It's another way to look at it. So if your matrix isn't a square, you're actually going to switch the shapes when you transpose, which is also useful. But linear unbiased estimator, what's bias and variance? Well, one thing you're often trying to minimize, especially in terms of regression problems, is a mean squared error. We square the error. Well, there's lots of statistical reasons, but essentially, like it's just a way to normalize the distance, regardless of if it's negative or positive. It's just sort of the absolute heuristic of distance between your target and your prediction. And it turns out that mean squared error is actually a composition of bias and variance. Variance plus bias squared, I believe. And so because of that, you always have a trade-off between bias and variance when you're doing machine learning or any sort of modeling. And this is sort of an example of, a very classical example of bias and variance. Of course, if you have no bias, you are average. Prediction is precisely on the average actual target. You have a high bias, you're far away, etc. And you can also view the mean squared error of linear regression as a sort of error between each point in the line summed up. One thing I wanted to touch on here is regularization. We talked about L1 and L2 distances a little bit ago. One thing I wanted to sort of add to this is, in addition to our sort of standard argument formulation of linear regression, we're trying to minimize the mean square error. That's this middle part right here. So what we already went over, we can add things to this minimization scheme. So let's say we also want to minimize the absolute value of the parameters we're finding. That's this operation right here, multiplied by some lambda, which is what's called a hyperparameter. A hyperparameter is something that the user has to choose. We're not actually going to explicit or find it through an optimization scheme. It's sort of you have to choose it as the designer of the algorithm. That can make them difficult to choose. There's some strategies there we can talk about. But by sort of trying to also minimize the value of each parameter we're finding, L1 regularization has this neat party trick, which is it makes a lot of them zero. So the solution is very sparse. That's important from an interpretation standpoint, because if some of your parameters for linear regression, for instance, in this car data set, were zero, it implies that that isn't important for predicting the price. So if it happened to zero out the cylinder for some reason, maybe that doesn't make sense, but it might tell the dealership that that isn't actually an important factor in determining the price. So it adds at least a small level of interpretation. It's also a way to add bias to the solution, maybe in a way to reduce variance. While that doesn't necessarily scream like it's a beneficial thing, the overall mean squared error can still go down, even though you're increasing the bias of the solution. And then, of course, instead of L1, you can do L2, which is you minimize the squared of each parameter. You might think that has the same party trick, but it happens to have a slightly different party trick, which it just leads to smaller parameters on average. It doesn't lead to as sparse solutions as L1. L1 is referred to as lasso regression, you may have heard of. L2 is referred to as ridge. Of course, you could do L3, but no one really does that. What's more common is to combine them. So you have lambda 1 and lambda 2. And that's called elastic net. And so in that way, you're going to enforce small parameters. Maybe that helps in some regard, and maybe you also want it sparse, so it's interpretable or something. What's important is regularization isn't just something that we can apply to linear regression. We can apply these types of cost terms to the loss functions in our machine learning algorithms to enforce the same types of trends in the solutions. In particular, the sparseness is kind of nice because one, you can run your mammals faster on your computer if they're very sparse, and two, they're kind of more interpretable if you look at them. This is just an example of the objective here is I took the MNIST data set and I threw out all the numbers that weren't 0 or 1. So I'm building a binary classifier here with linear regression. So if it's over some amount of the line, I'm calling it a 1, and if not, I'm calling it 0. So I do an ordinary least square, that's OLS. And I'm training this on the training set, and then I'm evaluating it on the test set, which is sort of something you always see. Well, I want to just point out that the average RMSE, so it's a root mean squared error, have the same monotonic trend as mean squared error, is 0.13 for OLS, even though this is the best unbiased estimator, linear unbiased estimator possible. Yet we've found a linear biased estimator with actually less MSE in terms of the ridge and lasso regularization. So by adding some bias, we reduce the variance enough to actually reduce the total error. Additionally, we've gotten some interpretability out of it. The best performer was lasso in this case. If we look at the, this is sort of plots of the parameters that the operations found, it sort of, we can see that lasso is very clearly looking at the central position of the image, which is sort of where a 1 would be quite different from a 0, which makes sense, right? So it's added some interpretability to our process here. Rich sort of found a similar solution, but it's not quite as drastic. Of course, OLS also found high parameters there, but there's sort of larger ones everywhere as well. And just to confirm that the party trick works, we just calculate the percentage of zeros here, and that's this thing on the top right. Any questions about? This is in one of the notebooks actually, so if you want to mess around with it, we will look at it. So now we're gonna move to neural networks. The fun thing about neural networks is that they're just linear regressions. But they were inspired originally by the human brain. And so the idea was we'll abstract neurons into some sort of node, and just like there's connections between neurons and axion, however that stuff works. It's not something I'm an expert in. Instead of a action potential, we can sort of just numerically model thresholds. So if like the sum of the inputs into some node is exceeds some value, just like the sodium potassium pump is going to do an action potential, we can sort of fire it and move the signal forward. But I think all of that is sort of even more confusing than what's actually happening in a neural network. In its most basic form, of course, the input is a vector, let's say, and these sort of middle hidden states at each step are a vector, and the output's going to be a vector, but what's in between those? And that's just the weights of the matrix. So there's these edges, and the operation is a mammal. So basically, if we were to model this sort of schema here on the left, our input X is dimension 4, 4 by 1 in this case. And we have this weight matrix W. And the operation to move to the next step is just mammal. So we just do Wx equals Y in this case. Oftentimes you'll see bias terms added to the layers of neural networks. You can also add biases to linear regression, which will make it so that it doesn't go through the origin. In much larger networks like transformers, typically they actually don't include a bias, and so I often gloss over them, but they're there. So it's just another learnable parameter that we add to our result instead of multiplying. But I guess I want to linger here a little bit, which is just like we can use permutation matrices to rearrange our networks, if our weights have a different amounts of rows and columns, we can sort of modulate the input in a way. So if our input is some X, and it's, let's say, 1 by D. So D is going to be our hidden dimension. We'll just refer to it as that. If our weight matrix is D by D, this is going to maintain the shape of our input after the mammals. XW, the output of this is also going to be 1 by D. But of course, if our weight matrix was not D by D, and it was instead some D by, I don't know, let's just say C. And C happened to be quite a bit larger than D. This is sort of going to expand our input into a much larger vector through a completely linear operation. So some linear combination of operations, addition, multiplication. And that operation is sort of the same as a linear regression, except we'd be moving up. So in the case of linear regression, when we did MNIST, we were sort of projecting 784 size vector down to size 10. So you're making it smaller. But we can go the other direction too. So we can have many more parameters. But this sort of size engineering here is really important because it happens to be very advantageous to project your input up to some very large dimension and later move it back down when you want some answer. It's an interesting fact that the sort of nearly orthogonal subvectors you can shove in a vector sort of scales exponentially with this value of D. And so sort of the number of concepts you can shove in this high dimensional vector space doesn't scale linearly with the size of D, it scales exponentially. And that's why it's beneficial. So there's some trade-off between the compute, how big can you make it, right? And inscribed value. So how are we going to train these things? Well, I'm mostly going to be talking about supervised learning, although one key step in transformers is something called semi-supervised learning, but that's kind of just a misnomer. It just means that we're not picking the labels directly as like the price of a car. It's assigned randomly. We'll get into that, but basically it's just supervised learning. And the objective there is, of course, to take some sort of set of inputs that all map to, in the classification case, a discrete set of categories. So dog, cat, chicken in this left case. In the regression sense, it's usually a continuous number. So that is more in line with the price analogy. In either case, the supervised learning sort of strategy typically is to input data into your neural network, get its prediction. Initially, this will be very bad because the network is randomly initialized, but then you will compare your output to the real answer with some error function, which you call the loss function. Error sort of something you want to minimize, right? You want to reduce the error, so you minimize the loss function. And you're going to update the weights to do that. And that's the most basic form of supervised learning. One really important concept in supervised learning, but just sort of modeling in general, is this concept of under and overfitting. And so some things are not linear, it turns out. They have distributions that aren't precisely modeled by a line. And so this is the case in the left example. When we use linear regression to fit this data, we get maybe a good answer, but not something that is really following the underlying distribution, even though it's a little messy. And we call a good solution, maybe it's a some quadratic, right? Because it sort of looks like it's following the distribution. We can measure this quantitatively by the mean squared error and some other properties. But what's unfortunate is that on the right-hand side, this is actually the most minimum mean squared error. Like it's doing the best job, right? It's really getting into the nooks and crannies of all the data points. The issue with this is that when we try to use this function on data we haven't seen yet, it's not going to fit those nooks and crannies of our data points. It's not going to perform very well. And so it's important to sort of segregate our training process in an attempt to be able to gauge overfitting. Typically, you're dealing with overfitting, not underfitting. And so our strategy uses evaluation data. You make some splits from your data, and you sort of put them in a safe. You never look at them until you're only evaluating, at least for the test set. One other thing you can do is have a validation set, which is sort of you'll periodically evaluate your model in the validation set throughout training, and that lets you decide when you're basically what sets of weights you're going to keep for the neural network. And so here on this plot on the bottom, we see that we have at some point we have both losses, both errors for the training and validation set coming to some minimum, but then eventually our model starts overfitting and the validation set gets worse. That's a really clear indicator that sort of the best weights for generalizability in this model and data schema is at that point. And so we want to throw out the weights after that. We'll use those instead. So just some basics of loss functions. We've already talked about mean squared error, but there's lots of variants to it, like root mean squared error, mean absolute error, or L1 versus L2 losses, right? And those are typically used for regression tasks. By far the most common loss function for classification tasks is cross entropy, which is shown on the right side here. And so we're sort of just comparing the true probability, which is going to look something like, we had three classes. We would label, and let's say this is the MNIST. So this is our inputs. Literally, this image here is a Q. Our label here, I guess that means there's 10, but it's going to be 0, 0, 1, 2. Not going to be a 2, it's going to be a 1. And then 0, 0, 0 all the way down. And so that's how we encode the label here for a 2. This is called one-hot encoding, by the way, which is where you take a set of categories, and if you have 10 categories, n categories, you make an n-linked vector, and then each one of those gets a 1 in that spot. In this case, the 2 maps to the not the 0th, not the 1st, but the 2nd indice. So that would be the true probability. And then our model is going to predict also a vector of size n, but these are going to be continuous numbers. And we're going to have them normalized in some way so that they add up to 1. So it's going to look like a probability distribution. Now, if our model's done an okay job, maybe it's something like small probabilities here, and then in this spot, we have like a much larger probability, like 7, and the rest. The rest of these values actually don't matter for cross entropy. For a specific example, you're just comparing these two numbers, this 1 and this 0.7. And if we look at the log, natural logarithm usually for this function, we'll notice that as this value gets closer to 1, so this would be the x value, the probability that we're inputting, the log of it is going to get close to 0. And so what we're actually trying to do is minimize this log qx. And that's why it has a negative sign here. Because this is actually going to be a negative value. Basically, when the probability is low, in the end, our cross entropy is going to be much higher. And if it is higher, our cross entropy is going to be very small. And we want this because this is basically our error. We want to minimize the error. You see the sum here because usually, well, it's actually true that you could technically have a continuous value in this left-hand side. It's just less common. But normally you're feeding more than one example to a model at once, and so you do need to sum the answers or mean them in some way. But that's a very basic introduction of cross entropy. Cross entropy is for classification problems, and yeah, like all the loss functions, you're trying to minimize it. Here is my one slide summary of gradient descent. Essentially, we have a very high dimensional landscape of numbers, which corresponds to our weights of the neural network. And we know what all those numbers are. That's good. But we don't know what they should be. And because we're going to be very careful to only do differentiable operations in our neural networks, we're going to be able to track the rate of change across our entire network with respect to the loss. And so we're going to input and get an output, compare that to the true value, and that's going to give us a loss value. So if you take for granted that, that means you can find the rate of change of that loss value, or in other words, the slope of this gradient. Gradient is just higher dimensional vector from the derivative. It turns out that that gradient is going to point in the direction of the steepest ascent. The gradient is going to point at where the loss will increase. But if you remember, we're actually trying to decrease a loss. So we'll just go in the opposite direction. It turns out that that will minimize. And so that is a core concept of gradient descent. So if you take for granted that, we know where all the weights are. We want to move them, but we're not sure how. But we can figure out the rate of change by looking at the loss. It means that we can move in a direction, move and update our weights, and sort of provably the loss will go down. Now, there is a lot of details here to make this work better. One question is, okay, for one input, how far should I move the weights? Should I move a lot or just a little? And so that value that dictates that is something called the learning rate. And again, it is a hyperparameter because the model is not going to find it for you, something you have to pick as the machine learning engineer. And so it's sort of something that can be very important because the right learning rate will lead to a quick and stable convergence, whereas a small learning rate, you'll kind of get stuck. And a large learning rate, you might overshoot. That's sort of this thing on the bottom. And there's lots of optimizers that incorporate these characteristics. There's stochastic gradient descent, SGD, you'll see in PyTorch. By and large, the most popular one is called ATOM, which I forgot what that stands for actually, but it basically incorporates other orders of the derivative to model things like sort of like a momentum. So like, are we, if we go in this direction, how much better are we really getting over time, right? And should I really start moving a little faster here, or is it worth it to back off a bit? So there's things like that, but almost always you can just use ATOM. And it will work fine, but there are, again, a ton of variants. So back to MNIST, basic problem formulation. Again, each image is 28 by 28 or 784. And the basic objective is to map a 784 size vector to a dimension 10 vector, where the largest value in that size 10 vector corresponds to the number in the image. And so if we start at 0 and go 1, 6, that means we actually want the largest number in this vector to be here for this problem. That's what we're trying to accomplish here. And so how are we going to do that? Well, again, we tried linear regression. The test accuracy is only 85%. And I just wanted to highlight sort of the characteristics of sort of the lines that it builds for each class, which are sort of interpretable. So yeah, again, here you can kind of see 6. Maybe this is a 7 and an 8. It's cool to look at this stuff and see what's going on internally, I think. There's contour version. Again, this is in the notebook, so we can like kind of go over this. One approach, maybe we don't need a neural network, right? What if we just took each class, let's take all the zeros, we'll flatten them into one big vector for each one. So let's say there's 1,000 zeros. They're all 784 length vectors. So that X matrix is going to be 1,000 by 784. What if we just averaged across all the rows, which have one big column? It's going to be 784 long, and it's sort of the average conglomerate of all the zeros. And then what if we just used our toolbox of vector similarity heuristics? When we input a new example, we'll just see which of these vectors is closest to. So we'll have one vector over here for 0, and in the latent space, we'll have another one for 1 and for 2. Except instead of learning this latent space, we sort of just built it from the training data, like directly. And so we can just do this. And I tried cosine similarity, I tried the Euclidean distance, I tried dot product. And again, sort of the most effective is a cosine similarity, since it's normalized, it's sort of the easiest to work with. It gets us actually 82% accuracy on just by doing it in a simple way. And the decision boundary it sort of builds, I think, can be interpreted kind of like this thing on the left, which is it's straight lines in between our averages. Our averages here are these like C1, C2, C3, and sort of whatever we're closest to is what we'll get. But again, like we said, not every decision boundary should be linear. Some things are non-linear. And so this is just, again, the decision boundaries of this method. So instead, why don't we actually apply what we're learning about neural networks, and let's actually do a couple linear regressions. But in the middle, we're going to add this nonlinear activation function. And there's sort of this neat property that if you do these things together, you can almost model any sort of type of decision boundary, any weird shape you might need to have. And so this GIF on the right is a good illustration. This logistic is similar, is like classification, but again, it's in a linear way. So it builds a very simple linear decision boundary for this curved sort of data set. But in this multilayer perceptron, which is a neural network, we're actually able to build a nonlinear function. Turns out that multi-layer perceptrons, this is a more than one layer neural network, more than one linear layer stacked together with activation functions. So it turns out 2-layer multi-layer perceptron, if you let the sizes of these weight matrices be large enough, they can model any continuous multivariate function. There's a lot of assumptions that go with that, like, can you actually find that solution, et cetera. But in principle, this is a universal approximate. Find any continuous multivariate function you could ever imagine. Much more recently, they figured out at another layer, right? This actually can model any multivariate function. It doesn't even need to be continuous. You can have big jumps and gaps and anything weird like that. So multi-layer perceptrons are kind of magical in that way that if the capability to model anything, if they're of sufficient size, you just have to be able to find a solution. So the job of a machine learning engineer is really figuring out how they can engineer the depth and the width of different types of neural networks in ways that sufficiently model the data and then can run in your computer convergent. One other thing I wanted to mention just really quick is that especially important for like things like PyTorch, which is multi-layer perceptrons really only act on vectors. You'll notice whenever we're talking about MNIST on this stuff, the basic form is a 20 by 20 matrix, but we always flatten it. That's because MLP really just works on a vector. And so if you fed a 2D matrix into, or a higher dimensional tensor into a linear layer, multi-layer perceptron, it's only going to do operations over one axis of it. And so if you had like several columns in your input, the MLP or your neural network is only going to model this independently, all in the same way. You're applying the same weights, but they're not like looking at each other. And it's sort of a big issue when you're dealing with 2D inputs because you actually want everything to be utilized in your answer. That's just a side note. Again, activation functions, by far the most common, I guess, talked about activation function is ReLU. Rectified linear unit, the function of ReLU is simply the maximum of 0 and the number you put in. So that means below 0 for the input, it's just going to be 0. This is clearly a nonlinear function because there's a jarring kink right in the middle. But this is sort of our, and this also has the best analogy to brains, right? It's like if the sum of the input doesn't exceed some threshold, the neuron doesn't activate, nothing gets sent. It's like it's a 0 signal. But if the conglomerate input is large enough to exceed the value of 0, then the signal does get sent. And so I think that's mostly where the analogy comes from. But there's also a whole bunch of other activation functions. This is a cute little cartoon on the right, which showcases some of them. The most important ones to know about are sigmoid and softmax, which I can talk about in a bit. But you'll also see these things like GLU, which is essentially some other continuous function, but it looks like this. So it allows a little bit of negative. But in general, it doesn't matter that much which one you choose for your network, but you'll see like tangent ReLU a lot, GLU. And so those are the major components of the multi-layer perceptron. It's a linear layer, activation function, linear layer. Again, multi-layer doesn't really mean only two. You have layer, activation, layer. And as you start to stack that a lot, you start to move from machine learning into maybe call it deep learning. I don't know where that threshold is, but basically a larger network would be a deeper network. There are lots of other types of layers beyond this linear layer, which is just a matrix. It's a matmul. Again, a linear layer is, of course, just a strategic matmul where you're going to learn the parameters in order to augment the input data in the right way. But other types of layers are also useful. So different differential things we can do. One thing is we can normalize the numbers, that state of the network. There's lots of different types of normalization. The most common are batch and layer norm. We haven't really talked about batches yet, but the layer norm would simply, we had our 784 linked vector for MNIST. We would subtract, first of all, we'd calculate the mean and standard deviation. And then we would take our input. Usually it's actually, what is it, mu and mu for mean, yeah. Mu for mean. We'll call it sigma for standard deviation. To do x minus mu over sigma. Very common way to normalize, get everything in a more appropriate distribution, perhaps. What's also common in layers that you'll see in PyTorch is they'll actually be this plus some, let's call it lambda, which is, this is size n, going to be another size n vector, but these are actually all going to be learnable weights. Another component of learnable stuff. So it's like the normalization is dependent on the data, but then also what we've learned how to augment it with. That happens to be really useful. It's just one example. Another type of layer that you'll see a lot is dropout. Dropout is an attempt to prevent a neural network from overusing neurons under the intuition that if it uses some neurons too much, that it will sort of rely on them too much and then overfit maybe. And so what dropout does is sort of randomly acts out some of the values of your latent variable. And so let's say our input was X again, and it was 1 by 784, and our weight matrix for our model happened to be 784 by 1024. We're doing an up projection, we call it. We do W. XW equals, let's call it X1. Is it going to be shape 1 by 1024? And then maybe at this stage is where we apply a dropout. So what would happen is we have, this big array of numbers, big vector. If our dropout was 20%, we just zero out 20% of these numbers randomly. Every forward pass. Every time we input data, we're going to randomly do it. During inference, when we use the model, we're not going to do this because it's going to prevent better performance. But it's sort of very useful for overfitting. Another strategy for overfitting, by the way, is like we've talked about already, regularization. So we can add the L2, the ridge regularization, to prevent values in our weights from becoming too large on average. And that's one way we can also sort of try not to rely on one too much, prevent overfitting. So before we combine all the layers together, maybe it's a good time for like a small break. I need some water for sure. So let's just reconvene in like 5 minutes. Sound good, everyone?
Sure.
Okay. See you in 5 minutes. Yes.
Yeah.
Oh,
Yeah. I'm gonna give a talk in my seminar in a couple of weeks. Like you came to Logan's, right? Forget if you did. It's at 3:30. You can join on Zoom if you want to as well. I can send it to you.
Yeah.
So I'm
Yeah, I didn't. I don't.
When do you fly out?
Charged for a while, like I said, it was next time.
And then I didn't have it plugged in at home overnight, so I just got the notification a few minutes ago that it was gonna shut down.
I was in like 5 minutes into my notification. And I was like, oh, really?
Is that what you're talking about? Good. And
I don't remember, but I'm a little, because it's like, more people have to listen.
yeah. So how did you pay for it already?
I like paid for it out of pocket. I'll
Okay.
hopefully get one.
Gotcha.
But,
Did you see Katie's comments and stuff?
yes,
Okay.
yes.
What did you think of like the revisions and stuff? I haven't worked on it in a little while, but.
Yeah, but she said, they said,
Uh-huh. So, still, I think that's gonna take.
Try to get into it.
So like, we don't have to worry about that too much right now, I think. Like, soon we. Feel that out, but I think over the long.
it's like, okay.
Yeah, and getting like, much stuff working. So I can also. Get some. I'm also doing one thing, like, hopefully, so it can be for the paper as well.
Pizza.
Just share them. We go down,
But I'm using babies. Pretty bad around there.
my ranking.
Okay.
All the undergrads will allow. So
That's fine. I like them.
Yeah.
Nice.
Those are just.
Yeah.
But. So
Yeah.
everyone has to.
It's legally usable.
I send you a link. Can you send it out to the participants? We want to. This you attended.
Yeah,
Wait, what? Oh, no. Oh, wait, that's your account.
Yeah.
No, but I'm using these snacks as a laptop. Yeah, it's just, I want. Oh,
sorry to come into your laptop.
No worries.
If you want to,
maybe we can
You
try
wanna
it
use
again,
mine?
or try yours again.
it's not working, we just did, but we can try.
Yeah.
I mean,
I don't.
It's
mind.
fine. I mean, I would need it when he's like.
Yeah, yeah,
the-
yeah,
Yeah.
Maybe break in an hour for lunch.
we'll have lunch first before the notebooks, yeah. So then maybe we can get someone to figure it out, right?
Yeah.
Has it been 5 minutes? Probably, right?
Yeah.
Well, first thing I want to take care of is, we wanted to document who showed up, which is useful to see what our turnout was. I think Julie, right?
Yeah.
So Julie, yeah, okay, got it. I'm just gonna paste this in the Zoom chat, Yes, I can. And if you guys. Use some other mechanism if you're not on Zoom.
Just the slides, you mean?
Oh, I'll be sending the slides, I'm just, no, it's a link to the document who came, they're just gonna. Her name in, I guess, Zoom is so wacky.
They changed
I
a lot.
blind.
Did you get it?
Oh, we have a question from Mark. How do I tell them I'm not stuck in a local minimum? We need to make sure it's a low learning rate, look at training loss curves if there are other means. Yeah, the hard thing about the loss weight landscape is that we're not actually calculating it for more values than the loss. So we actually don't know the surrounding loss values around our point, we sort of only know the direction we should go in. So usually when we're optimizing, we're not explicitly calculating the entire loss landscape. That makes it difficult to tell if we are in a local minimum, if not impossible. And so one way to just try and avoid them in general is something called a learning rate scheduler, which is instead of picking some random value for a hyperparameter, maybe you've actually tuned the hyperparameter learning rate through some sort of cross-validation. We can talk about that if people are unfamiliar, but maybe you already found a good value for that. And so maybe you'll actually add a learning rate scheduler. So I'll draw it on the iPad so everyone can see. Where is it? Okay. So maybe we'll schedule the learning rate so that throughout our training process, it's common to have like a warm up. There's some, maybe we can start at 0 learning rate. We're fit on the first batch or something. We're just very small and then slowly increase it over the course of the training. Maybe this is like 20% of our training process. To get to our maximum. And maybe the learning rate we found that was optimal is actually somewhere here. So we're actually going to go too big first. That way we can do any big jumps that are necessary, or we sort of settle down into a local space that we actually need to converge more carefully into. And maybe then we'll, over the rest of the 80%, slowly go back down to 0. And so by doing this, the idea is that, one, the learning rate isn't too big when you start, so you don't instantly overfit on some your initial batches. 2, by going larger than you think you need to, you don't get stuck too early. And 3, by slowing down near the end, you don't jump out of something that's really good. All of that is very hand wavy, and it's sort of more empirical than theoretical, I think. But it does work. That would be my first attempt at an answer there. So before we move forward, any other questions in Zoom or here?
So you just described it sort of like surveying the landscape in a way, right? To make sure that you're not in a hole, that you're not moving out.
So that's one way you could do it. I think that'd be more difficult though. I think what this is more of like setting us up not to do that. It's sort of a process that in general will not put us there, although there's no guarantee that it won't. Again, the weight landscape of a large language model with 1 billion parameters is 1 billion dimensions wide. I have a hard time visualizing that. I don't know about you guys. So even if you were to calculate the loss landscape directly, like you're literally just sampling random weights. You're just augmenting all the weights randomly and calculating what the loss is for those for some set of inputs, and then you build your landscape. Even if you were going to analyze that, you'd have to analyze some lower dimensional projection of it, like principal component analysis or something, at least if you're going to do it visually. All I have to say is it's not worth it. Like, it's just better to try and avoid. Yeah. Anything else? Okay. I just wrote this here so I don't forget. I basically want to draw an analogy between our mean vector classifier experiment and our multi-line perceptrons later. But I guess this is maybe not the best time. So we were just talking about other types of layers beyond linear layers. Linear layer is our bread and butter. It is the fundamental component, but again, we need activation functions to move away from just some linear regressions to be able to do nonlinear dynamics. And then we have things like batch norm and layer norm, which help keep our values normalized, our convergence stable during training, and dropout helps prevent overfitting. And so if we combine the techniques we just talked about, we apparently do not get that. Let me see what's going on there. Apparently I was not ready for that. So again, so simple linear features are powerful. Sometimes you need nonlinear features. Sort of already touched on this, but like by projecting up and having activation functions, we can move away from linear features and start to do sort of have the model do feature engineering for us. Basically, do weird combinations of our input values. You know, for instance, maybe the valuable input to model our system isn't A, B, C, D, or E by its own. Maybe it's actually A, D, and that would be a linear combination, and that means our linear model might model it well. Let's say there's a extremely high correlation between A, D, and our Y answer. Like a linear model here would work very well. But what if the fundamental correlation, for some reason, maybe this even has to do with, I mean, we're measuring a physical process, and there's a law of physics here that involves a quadratic. I mean, maybe the fundamental correlation happens to be between A squared and E. In this case, our linear model will fail, but in some ways, we can actually still use a linear model if we just add A squared as a feature. If we explicitly added squared feature there, again, we had to do that beforehand, but now we could use a linear model to do a linear combination of A squared and E. So there's things you can do this. There's this function in scikit-learn called polynomial features, which essentially adds to our feature vector. Maybe that's MNIST, maybe that's our card data set, but it will add every quadratic combination of the inputs. So it just multiplies them all together, but also you could have higher degrees, so you can move to cubics and etc. But the issue with just doing this in general, like why do we need neural networks at all? The reason is you don't know what you should put here. What is the high enough degree that you should go to? Is it a fourth? Is it fifth? You actually need the 10th of A plus minus C, 7C plus AD squared. You know, I don't know. The point is we don't know. And what's cool about the optimization process and projecting up with neural networks is they can find these types of combinations that are important. I guess that's the point here with representation learning. But also we're going to talk about token embedding, which is like a direct way to literally learn all the features of our input, but we'll talk about that in a bit. Again, either project up or directly learn via embedding process. So I just wanted to highlight a simple multi-layer perceptron combining all the layers we talked about. So this is something called torch summary, by the way. So it gives you a nice lay down of what every sort of all the layers in your network and what the shape of the latent is at every position. Perhaps it's hard to see, but basically we start with we start with 20 by 28 for MNIST, but then there's actually this flatten function which flattens it for us into 784. And then I should be drawing on an iPad, but basically then we have a layer norm, which normalizes it. Then a linear layer. After that linear, it turns out that the hidden size of our linear layer was 1024. So now our vector is 1 by 1024. Then we do ReLU, then a dropout, then another layer norm, etc. So the order is typically layer norm linear, ReLU, or activation, then dropout. You can repeat that, and then eventually we have a linear layer which is 1024 by 10. And after that matmul, our output vector is size 10. From there, the largest value in there is our prediction. But we still need to model that in terms of probability distribution, right, in order to use our cross entropy. So I guess one thing I should describe is softmax. Softmax is just a way to turn a vector into a pseudo probability distribution. It basically just enforces that everything between 0 and 1 is sums to 1. It's a different type of activation function. There's also something called sigmoid. I'm not going to just write them out. I don't think it's important to know. We look it up later, but it will actually just model any scalar into between 0 and 1. It sort of squashes them. So those are ways we can sort of use use this final map mole, which is going to be a messy output. It's going to be a bunch of numbers. And again, we know that max number is our prediction, but they're sort of messy, right? They're not unscaled. So we can use a final activation function to make them all pretty probabilities. What's on the right is the just sort of a projection of this decision boundaries for MNIST in this case. If you remember the ones we had earlier in the average case, I mean, they literally looked like the digits, right? Because that's how we built them. And the linear regression cases, they were a bit more abstract. But this sort of illustrates the sort of highly nonlinear dynamics of decision boundaries we curate with multi-layer perceptrons. This is a 2D projection of the very high dimensions. So it's even more, complicated and weird in high dimensions. And it does a much better job than our averaging of linear regression. It's a 98% accuracy in the test set versus 85 and 82%. Okay. I guess I already talked about that. Sweet. Okay. Well, yeah. Let's touch on it again. Just to stress that if you have a 2D input, you have to either flatten it, which for a very large 2D input is like absurd. Absurdly large vector. And that means your weights for your multi-layer receptor has to be equally as large, right? Because the shapes have to match up. And so sort of if MNIST for some reason, if the images in MNIST were massive, 2800 by 2800, not 20 by 28. I mean, they're 4K images, right? And we had that big matrix. And we wanted to use a multi-layer perceptron to solve the problem. We would have to model every single. It would basically just be, you'd apply a multi-layer perceptron independently to each column. And then you would get an independent answer for each column. And then perhaps you would have to just average those up and see what you get. But what was clearly just not advantageous here is like, what are you going to get out of this column? This column is going to be like all background. The answer here is not going to be informative. What the model will probably learn to do is put an even amount of probability here so that it basically doesn't influence the decision. But and so it would try and make most of its decisions by looking at this stuff. But clearly we can see that we need to leverage the entire context of our input in order to fully understand what we're dealing with. One approach to images was convolutional neural networks, and those work really well. And actually, convolutional neural networks work better than transformers on small images like MNIST in the very simple case. If you actually do pre-training, transformers are very good here. But so I just want to side note is that convolutional networks exist, and they augment some local context because they look at little regions of the image, not necessarily the whole thing. So that's one approach to this problem, but we want truly global context. We want to contextualize everything in our input in one network. Actually, no matter how big it is, theoretically, we need something else. And that is where attention comes in. Okay, attention is the beautiful part of transformers. It is what allows us to look across, say, L instead of D. So we're going to move away from, no, I mean, we can stay with MNIST. It's 20 by 28. Let's just say that that image is now L by D. In this case, L equals D equals 28. But let's just keep it as variables. And what I mentioned before is that basically, I guess this would be L, this would be D. I guess I was actually drawing it backwards, but essentially the multi-layer perceptron would actually look at the rows of something if we drew it in that case. The problem still remains the same, but we actually want to look across the rows and the columns. Our matrix is 2D after all. And so attention leverages a transpose operation to flip our input, and then that allows us to sort of multiply them together and end up with something that's L by L. This is really important because it allows us to sort of measure the similarity of everything. Sort of just trying to be abstract about it now, and then we'll actually go through the details. But then we have another version of the input, which we multiply it to get it back to L by D. So that's sort of this is sort of in a shape sense, this is what's happening in the attention operation. We're starting by L by D, we're moving to L by L, and that's letting us mix information over L instead of just D. So we're looking at that like global context. But then if we're gonna have like sequential blocks in a network, we usually want to have the input and output be like the same size. So we use V, in this case, we go back to L by D, and that allows us to have basically mixed information along L. We've exchanged context. We've done our networking, right? And we've gotten back to L by D. Cool. So that is like the core of the operation. The details of it is there's 3 weight matrices. Let's start the weight matrices for a second. Let's just what if we actually did like literally raw self-attention? We're literally going to attend something directly to itself. Let's say that input is X, again, it's L by D. So if we did X transpose, this means we have a L by D and a D by L. That's going to cancel out. We're going to be L by L, but like what does that look like? Let's assume L and D are actually different this time. So in that case, we'll be looking at the rows of X and the columns of X transpose. But because those were the same matrix, those are like the same things. And so the dot products or the vector similarity from the resultant MATLAB are going to be really high. And so our final L by L matrix is basically just going to be a measurement of the similarity between the vectors from X in a mirror of itself. What that means is these values along the diagonal, which is where I equals J, so the row and the column came from the same place, they're going to be really high because they're the same thing. Of course, they're very similar. This softmax operation, again, is a way to make this nicer to look at, right? Instead of some unscaled dot product, which we have the general intuition that bigger is more similar, we're actually scaling every, let's say, column to be between 0 and 1 and to sum to 1. So that's going to mean that like these values are going to be like very high, 0.9 or something. And everything else here is going to be some smaller value, unless for some reason there were duplicate columns, X or something. And so this L by L is like a self-similarity matrix. It's like looking itself in the mirror, and what that results in is very high values in the diagonal. And then if we multiply this by X again, so there's no weight matrices for B. If we want to get back to L by D, we just had X transpose and then X again. So that basically, again, it's going to move us back to L by D. But because we didn't augment X at all before we multiplied, and the values are very big along the diagonal. It's almost like this looks like the identity matrix. Very close to it. Ones and zeros almost. And so our output is almost going to be exactly X. And so that isn't very useful, right? Because we want to do something here. We're trying to engineer our features, right? We're trying to include our global context. We're not trying to just use attention as an identity function. That's not very useful. So that's where the weight matrices come in. We're actually going to learn different projections to learn matmoles of X, 3 different ones, Q, K, and V. And that's like looking at the same thing through a different lens. In that way, Q, K, and V are actually going to be quite different. And the input and output of our attention function are going to be different. They're going to be modulated. And because we're doing this a learned way, we can perhaps assume that it will be helpful. And so the weight matrices are typically all D by D. Our input is L by D. And actually, I shouldn't, the weight matrices actually should start with W here. Oh, wait. So let's call them WK, WV. And to get the queries, keys, and values, of course, we're going to do a matmul. And that is angry. And what are the shapes of all these, by the way? QK and V. L by D? Does that make sense? It's that simple trick that we learned before. So the size doesn't change at all. So now, again, we transpose K. And that, maybe we call this resultant matrix A for attention. And again, the A is always L by L. Because of this transpose operation. And so now it's like, here's one way to look at X, and here's another way to look at X. And now we look at the similarity. And what that means is the diagonal isn't necessarily the large value anymore. This is sort of where the semanticity or the value of large language models or transformers in general, for proteins, often this is often just try to look at the protein in like a spatial way. So it's almost like sometimes where things attend highly are not necessarily where things are the same, like an alanine and alanine for a protein. Maybe it's actually where things are close in 3D space, maybe not in 1D space though. That's one of the neat properties of protein language models and using attention. In natural language, the high values of attention typically correlate to things that are related grammatically, again, semantically or some underlying meaning. Even though the initial token embedding from X weren't the same thing because we did this big matmul, right? And then again, we go back after a softmax to normalize it and just another matmul V. Importantly, we realized that dot product wasn't a perfect similarity heuristic because of the magnitudes of the vectors that are sort of involved in the dot product, again, causing similarity in the magnitudes. So we sort of divide by what you might interpret as the average magnitude. I mean, that isn't quite true, right? But we just, this D is, so if it was L by D, we just divide by the square root of D. It sort of removes the magnitude a bit. So it's sort of more normalized in general. It basically just infers that it makes sure that the softmax is numerically stable because there's floating point operations happening here, so that we don't want the number too big. But it also makes the dot product a more interpretable similarity heuristic. Any questions? Okay, so that is the crux of attention, and the intuition behind it can go very deep. I mean, but essentially it's a self-similarity measurement. And it allows us to mix information across one axis of our matrix instead of just the other one. Another important concept is multi-head attention. So instead of an L by D, we pick some number of heads, N. Usually we enforce that D is divisible by N. Let's say there were 4 heads and our hidden dimension was 1024. So now our head size is 256. And then what we do is we reshape our X. And we're in tensor land. This would be L by N by H. So you'll notice the same exact amount of elements in our array are here. It's just that we sort of organize them a bit differently. Now we have L different copies of N by H's and L different matrices instead of L different vectors. what's important is that the operations of that Q, K, V, where again, matmoles are linear layer. So it's just like our multilayer perceptron analogy, the matmole only applies in PyTorch to the last axis. So basically what this allows us to do is build n different independent views of X. What it really is looking at different portions of X. And this, for whatever reason, is more effective. This allows the model to look at the input through more different lenses. And because we split it up, the D into n by h, and we don't literally just make different copies of D length, it turns out that this is basically computationally equivalent in terms of expense as a normal attention. And so it's used instead almost always. The only addition is that there's this weight matrix at the end, WO, usually is called, which is again another D by D, which just happens to, we just apply it after we reshape our output. So there's that final A times V that would result in a X2 or something, maybe we can call it Y. It's L by M by H. I guess D was the bad analogy, but no, actually, it's still D, but my bad. What we do is we have this final output, but then we reshape back into L by D. And because those were all processed independently, they're not like, the analogy is that they're not working together. They're not coherent. They're not aligned. And the idea of WO is after that matmole, it will everything straightened out. So that's multi-head attention. So this is by far the most common way to apply attention in a transformer. Well, now we've sort of gone over most of the components of a transformer. So what is a transformer? Transformer is a neural network, which is adept at augmenting and building representations of 2D inputs, matrices. It does that by incorporating attention blocks, which is everything I just mentioned. So learn matrices that apply QKV, and then multilayer perceptrons, which are just, again, linear layers without any fancy transposes or anything. And so the attention layer mixes information across, I mean, I've been using L, I guess it's N here, but usually are L. And actually it's flipped, but the point being is that attention mixes information across one of the axes of our matrix, and multilayer perceptron mix information across the other. And that allows us to process the entire input as a whole. Of course, many things are matrices like images, but we usually also encode things like text into matrices by giving each word, amino acid, token, a vector. And we'll talk about token embedding. But there's also other bells and whistles that get added on to the attention layer in the multilayer perceptron. Probably the most important is positional encoding. If there is a column in X that is repeated, it will have the same exact attention layout, I mean, just in a different order after our attention operation. That's because, again, the linear layer only looks at the one axis at a time. And so if they're exactly the same, they're going to be treated exactly the same. But even if there's a repeated word or token or whatever in our input, it doesn't mean they're the same because they're different positions in our sequence. And so usually we also add some sort of information that's related to the position in our matrix. There are ways to do this in relative ways so that the model can extrapolate to any L or any sufficiently large L to be effective. There's also direct ones where we literally just, we say, we're going to learn this vector, and this vector corresponds to the 0th entry, and we're going to add it always to the 0th entry. So that's consistent. There's lots of different approaches, but basically the way I've heard it said, the attention is invariant to position. So you need to add that in so that I can understand that. What that does is just influence the dot products, not only by the value of the token, but by where it is. So that's very important. The other thing that's important is layer norms, because there's a lot of a lot of floating point operations here and keeping things stable and convergent during our learning process is very important. So layer norms help with that. There's usually a layer norm, usually either pre or post norm of each of these blocks. So there's one either before attention, before the MOP, etc. And what you see on the, and there's post norms and thing on the left here, which is what they introduced in 2017, but usually it's pre-norm now. This other arrow, you'll see, not just sequentially, but also sort of sideways. It's called a skip connection. Skip connections, basically the input, if the input to attention was X and the output was Y, before we move on, we do X plus Y. Maybe that's X1 or something. We literally just add them together. From a feature engineering standpoint, that doesn't really mean much, but it sort of, it means a lot for the differentiable part of our neural network. So in neural networks, we have a forward pass where we input data and we get an output. But then the backward pass is when we look at all the gradients and update the weights, etc. And when you do skip connections like this, you join the gradients of those positions. And sort of like you just links the learning a bit. So the analogies are quite apt because they're very abstract and they also don't like mean that much. But what skip connections do is they make the lost landscape of a neural network much more smooth. This allows better convergence, right? I would much rather go on maybe a hike on the right, one on the left, maybe easier to get around and navigate. And I guess I had a slide on position embeddings. This is the most common type of rotary. Basically, we have this big frequency matrix scaled by cosines and sines, which of course are they repeat a lot, right? And so if you have some sort of scaled sine and cosine, the idea is that you can tell the absolute position of where you are, but also the relative position of where you are. And so this stuff is pretty complicated. And honestly, I forget the details myself, but I just trust that rotary embeddings work. And so rotary embeddings are the common approach. There's a really nice paper called Raw Farmer, so feel free to read it, but that's typically the approach. In particular, this is applied to the queries and the keys. That's the Q and K of the attention. So the information gets injected after those are formed. And so we build that similarity matrix with that in mind, but then we don't actually add the position embeddings to V. Of course, the V acts on the L by L, but it's not like, it's like we add position when we need to, and then it isn't there when we don't need it anymore. It's only needed for the attention, so that's where we have it. And there's usually a different, well, that's not, I guess I'll leave that tangent to be, but that's essentially rotary positional embeddings. And again, there's other types, which are less common now. And so how do we move from transformer to large language model? The answer is stack them together. The one transformer block is one self-attention, multi-head self-attention, and one feed-forward or multi-layer perceptron network. You put n of those together, you have the n transformer blocks sequentially, and that is a large language model. Another very important component is the token embeddings. And so this is the really important step and the sort of magic of like representation learning, which is words aren't numbers, right? The cat went to, I don't know, something. How are we going to represent these strings numerically? Of course, you know, in a computer, right, they live as some string of memory, but that this isn't probably semantic. Like we probably want cat and dog to be closer together than cat and the maybe. So we want to have value in there. And the idea is we'll just map each one of these to its own unique integer. So it's like there's a dictionary. It's like instead of a dictionary in the Oxford Webster dictionary, like words in definitions, you just have words and like a little token there, integers. So you like the is actually 4. and cat is actually 26. Turns out you can represent English pretty well with about 30,000 of these tokens. Much more common to have like 100,000 or 200,000 tokens in modern large language models, and that has to do with lots of different types of characters, and including other languages, etc. But basically, we'll have one integer per word or per unit. Maybe that's letters for. Maybe there's also letters in the LLM for protein language models. Of course, that's usually amino acids. The vocabulary is like 20 amino acids, 20 letters, 20 integers. But that's our sort of fundamental dictionary. And then we're gonna have another lookup table, which is just gonna be a matrix. This matrix is, let's say it's V for vocab by D. Again, so if it's English, maybe this is V is 30,000. But when we want to build the input to our transformer, we're just going to actually extract the row, the D-dimensional row that corresponds to each integer. So we're just going to index it. And again, that might be confusing. Like how could that be done simply? But like we were talking about permutation matrices earlier, and it's just like if you construct the right matrix of zeros and ones here, one hot encoded, that corresponds to your words that you want. You can just do a matmul and extract what you need, which is cool. And so you basically just stack those rows together to form your whole input. And then you have your L, which would be 4 in this case, right? 4 tokens by D. And by the way, if they're the twice in your sentence, you take the same row twice. At this stage, they're exactly equivalent. After position and attention and all this processing, eventually later in the network, they're not going to look the same anymore. Maybe they'll still look similar because they're both the, but at this stage, they're exactly the same. And this is how you go from text or any sort of token to a matrix. And the best part about this matrix is their weights. So again, I don't know what the 1024 numbers that represent the should be, but we can learn them through gradient descent. Because again, this layer, even though it's not a linear layer, and even though it's not some other thing, it technically is a matmul. So that's token embedding, and we already talked about positional embeddings and skip connection stuff. So if we add all that together, we have a way to go from text to matrix. We process that matrix, and then we're going to get answers out of it, and hopefully that's useful, right? So that's how we build an LLM. And this is some more examples about token embedding, more concrete example. I assigned a unique token ID to each token. Apparently it isn't a great example because 2 and demonstrate have the same token. So let's just not look at it too closely, but essentially we extract rows from our token embedding matrix, stack them together, and then we have a matrix, feed it to the model. So how do we train these things? These networks are often really big, and we design them that way because we sort of have lots and lots of unlabeled data. And that is convenient to do some sort of like denoising on. I'll talk about what that is, but essentially we try and leverage a concept called transfer learning, where we do a general task over a large corpus of data that sort of is very broad. And we hope that specific tasks we're interested in lie in that axis. And then what we do is after we do the very expensive step of pre-training a language model like this, hopefully we've learned good embeddings that we were just talking about. So like maybe the final embeddings after training, one of the examples that you see a lot is you have some vector for like royalty and one vector for like woman. And the idea is that if your space is trained well, sufficiently semantic, if you literally just add those together, the vector for queen should be roughly there. That's actually true. It's very close in most English language models. And so, and then that's in the input side, just the token embeddings, just that matrix. After you go through the whole model, that last instance state is going to be even more context dependent. But again, we have to throw my pen away. We have to learn these things. So how do we do that? The idea is, I'm gonna talk like what's called a BERT-like model. BERT is just a paper that came out, bidirectional encoder representation transformer. The idea is that this is the base LLM with all the math I just talked about, but basically the idea is the context is global. So all the tokens can look at all the other tokens. It's that full L by L attention matrix. We'll talk about another model in a bit that isn't like that, but the idea is we'll take our sentence like transformers are really cool. And maybe this is a very long, this is maybe even a whole book, maybe a whole passage from the internet, very large body of text. What we can do is take one away, some percentage of it away, and we'll add a new token called a mask token. This mask has its own position in the token embedding matrix, so it gets its own vector, and it basically represents fill in what goes here. And then what we're going to do is we're going to train our model to predict the words in our masks. In this case, we wanted really. Operationally, that works by we have our final L by D matrix from the outputs of our model. We somehow need to map this to L by V. V is our vocabulary size. We have another, this is a D by V matrix. Let's call this Y and O, I guess. Y, O, yo, is going to be L by V. And these are going to be unscaled predictions of every single possible value for each element of our matrix. And the largest value of that matrix is our prediction. So if the largest value of our matrix in the position where we had a mask is really, let's say, really good job. And of course, just like in our other classification example, we're going to softmax this so that it's a distribution of probabilities. And so language modeling is actually just a vocabulary length classification problem where we are mapping the positions of mask to the label integers for our tokens, which are one-hot encoded. We use cross entropy loss. It's just a classification problem. Except we usually mask out some percentage of the examples, and then we're going to average the cross entropy for all of those. Does that make sense? Any questions? Cool. We're going to classify the mask. Turns out when you do that enough, the model starts to learn, starts to look at, starts to leverage the embeddings in interesting ways and starts to encode information that starts to correlate with things that are actually useful in the real world. Classification, gradient descent, etc. Again, I have this example. We use the model. Of course, I love to use protein examples because I love protein language models. So here's a more discrete example where we have this input text. These are amino acids, and we mask out one amino acid. The amino acid that goes there happens to be an E, and it actually is much longer. I actually feed the whole protein, but we're just looking at a part of it. We token embedding, we feed it to the model, and here's real token embeddings from a protein language model. It's one of the smallest ones. And so, yeah, not super interpretable just by looking at it. Certainly not, but this is our L by D matrix. And our values just so happen to scale between -1 and 1. I didn't scale at all. It might be because this is right after layer norm, perhaps. So the first layer, we end up with two outputs. This is our output, the actual hidden state from the output, but then this is our L by L matrix in the middle of attention. And this model happens to use rotary embeddings. And so you'll notice that most of the attention values are larger relative to each other. So things around it. And that has to do with the position code. So things are typically looking in the local context because we're sort of enforcing that via the position code. You'll see that the CLS token and EOS token I didn't talk about those yet, but we usually add the start or end of input tokens so that the model can sort of better group what we're inputting. It's also helpful if you want to input multiple passages of text or multiple proteins, et cetera, into the same model. You can split them up by other special tokens. So the special token concept is also, I guess, an important thing to talk about, which one of them we already talked about was mask token. Typically, there's 4 or 5 of these in the model, but you can, like, in theory, if you want your model to do different things in training, let's say you wanted one model or one forward pass, you'd like the model to do mask filling. So you have a mask filling special token, you tell it to do that. It's like an instruction, and then the rest of them are mask tokens. Maybe the other, you have a special token that is for translation. So actually, in this forward pass, I don't want you to fill in the mask, I want you to translate from English to French or from amino acids to protein sequences, right? That'd be very useful. Of course, in the English case, the special token doesn't really need to be there because you can actually add just context, which is an instruction. That's called a prompt, right? We'll get into prompts, I guess. But so just looking at the attention is pretty interesting. But you'll notice that it's not just the relative position stuff. There's also highly attended sort of darker lines where things are attending outside of their local region. This one accentuates the relative position encoding, right? The average attention of this layer. So there's 6 transformer blocks in this model, so we have 6 different outputs. And so not very interpretable. Yeah.
You explicitly tell the model that when you see a mask token, you need to predict, or when you see, the end of sequence or the end of input, that's the end of the input, or is that just something that the model learns?
Yeah, your only real instruction manual is a gradient descent, right? So you just have to correlate the patterns of your inputs, like yourself, with what you want the model to do, and then you have to reward the model accordingly. So you have to give it the right labels, right? So no, you have to engineer that yourself. But in terms of like mask filling, typically like models, it's usually the only objective you're doing. So you don't like tell it anything. I mean, you just fill in the masks. You tell it when it did a good job for your gradient descent, and it will learn to do that. Or the loss would go up, and that wouldn't really work, right? Because gradient descent has to go that way. Yeah, does that make sense? Being on Zoom. Don't be shy, guys. Just texting. Are you guys on Zoom? Can you monitor that? Yeah. I don't know. Okay. And we apply that final linear layer, which is v by d, or d by whatever we did to get from the hidden dimension to the vocabulary dimension. And we use something called argmax. Argmax is an interesting operation. It's like if we had 0, 5, and 7. We took the max of this, of course, it'd be 7. We take the argmax of this, it returns the index. So it's very useful for figuring out what our prediction is, because then we can go back to that dictionary of tokens, because we have the integer that our model predicted. We can go to the dictionary and look it up and say, oh, right, that was an E. We actually got this prediction right. It predicted the amino acid as E in that position, so that's good. So just to reiterate, the argmax would return in Python, returning 2 here, because Python does 0 indexing, 0, 1, 2. Now, argmax is very useful in many applications of like in the internals of the model. You can architect many different types of things if you're allowed to use argmax, but unfortunately, argmax is not differentiable, so you're not allowed to do that. Very sad. But during inference, when you want to look at the answer, you don't need to use that to do gradient descent, or again, when you're just analyzing the outputs, not using them in a differentiable way, you can use argmax. Again, kind of got on this, but cross entropy loss, because it's just a classification problem. Okay, so moving away from BERT-like models, so those are called transformer encoders, but that lingo doesn't mean a lot anymore. But into GPT-like models, so these are, of course, everyone knows ChatGPT, but the only difference really between the models we just talked about with the masking and GPT is that we remove some of the context from the attention layer. So we're going to enforce that after softmax. we're gonna have some zeros in the upper triangle part of our attention matrix. The reason we do that is that we don't want our model to be able to look ahead of where it is. It's basically just a thing that we use to train it. So if we look at our example, if we're at the is position here, is can see life, life is. But it doesn't see anything beyond that. It doesn't see short or eat or data set or first, even though that's technically in the input. We're like keeping it from seeing that by zeroing that out. The reason this is useful is because the way these things are used to generation is ChatGPT basically has a beginning of sequence or whatever the start token is, and it starts and here's their prompt tokens. And it says, no, it's the user's turn. Here's another special token for user, right? But then it has an EOS, end of sequence or something. This end of sequence is trained to get mapped to the next token in the process. So instead of doing cross entropy over the masks and what you hid, it's the cross entropy between EOS and the token that comes next. So again, you know what went there because you knew when you're training these things, you knew the passage of text, you knew what went there. But you don't give the model that, you give that EOS, and you say, put what goes there. Wait, and that's useful for generation, but you actually train, the reason we have this extensive mask is because during training process, you can be training many different examples at the same time. So you have this token trying to predict, usually with special tokens, I mean, maybe you're not including that in the loss, you don't care, but like in this example, you'd be feeding in prompt and you'd want to get tokens out of it. What's interesting is because you have this attention mask, you can do that in parallel for every option in your sentence. So that allows you to have like L training examples per training example. You just sort of lets it train faster. But again, the causal attention mask is useful for this generation bit. That makes sense? Cool. That's the main difference. This is again going over autoregression. So some set of special tokens and conditioning through training processes, and then the model will map EOS to some token, and then you'll put it back in the model with a new EOS token. And so how expensive is this anyways? These map moles, I mean, I didn't talk about flops or anything, and I'm not a computer scientist, but I just want to highlight that the sort of the computational order of the transformers basically scales with the length of the input, specifically with regards to the attention. So you'd call the attention operation L squared times D. It does depend on D as well, but linearly, right? It depends on L quadratically, which is a problem. So as your input text gets sufficiently large, you're going to spend quadratically more compute to get an answer. There are so many tricks to deal with this now, like caching and caching the prompt in the system. Like obviously the AI companies have a huge incentive to make this cheaper, right? And so they do. And there are ways to deal with this, but essentially it's still a limit. Like if you want to model 1 million tokens, it's going to be a lot of operations, right? And that's even more so for quadratically increasing. And then it's important to realize that for the generation process, it's really OL cubed, right? Because if you're doing L squared every forward pass, you're doing L forward passes. I mean, just to contextualize the generation process, very expensive. And of course, so there's many attention variants which attempt to mix information across our L by D matrix. So again, what does attention solve? It solves the mixing across L problem. The MLP handles define is that the computational expense of multivariate perceptron is very minimal. It's very fast, for most things. But L can be the issue with large inputs, and so there are other types of more linear operation, so your linear attention or subquadratic. There's one application where you can actually do a fancy Fourier transform, and that's O log n log n or something. And it basically it mixes some information across L, maybe not as well as attention does, but it's better than just multi-layer perceptrons. And so I just wanted to bring awareness to the myriad of transformer variants and attention variants that exist, mostly to solve this process, not because they really perform better. You'll see the occasional paper like Mamba or something that comes out and they say, oh, this is actually better than transformers. And this is actually one of the big things with DeepSeek that blew up the whole stock market last year, because they invented an attention variant that was faster and a little better. Like definitively, not like, oh, that kind of works. And so that was a big deal because they're like, are we on the forefront at all? But yeah. And so but that mostly has to do with not the fundamental things we talk about today, but like how you deal with the memory caching on the computer side. Cool. Attention variance. So that was my talk. So I wanted to go over any questions people have. Maybe we can do questions and then lunch and then do our work or notebooks. Yeah.
The output part, this slide just a few ago.
Yeah.
And that process, I've read how that takes a lot longer. And I'm trying to understand that, why they're putting it back together and putting, at least with LLMs, the tokens back together is a more computationally intensive process or a lengthier process. And I'm wondering if that's also true with proteins.
So yeah, I think it's interesting. So
Read that, I'm not sure.
well, nowadays models do this like chain of thought thing where they generate lots and lots of tokens. But there's also, instead of just regurgitating tokens to get a better answer, there's these latent chain of thoughts where you iterate over something that you're not decoding back into tokens. So it's not readable, but it's a way for the model to think, right? This is in a sequential way. For English language model and multilingual language model, this final step is very expensive because the vocabulary size is massive. So I mean, this map model is insanely large. Like I mean, you're doing a 8,000 size vector times a 250,000 size vector across L time. So it's like L by that flops flowing point through. I mean, because GPUs are magical, apparently it's fine, but it is a much slower overall step than the other operations usually. So yeah, that makes sense. For protein language models, that doesn't matter as much because our vocabulary size is tiny, usually 20 to 30, sometimes a little more, but yeah.
Minuscule.
Yeah, very minuscule. Yeah. 20 versus even 20,000, 200,000, big difference. Anything else?
How will model understand the context of the sentence? For example, we have two sentences, and the first sentence is apple is tasty. So the apple refers to the fruit. And if the second sentence is apple just launched iPhone 17. So how will model understand that the apple in the first sentence refers to the fruit and the apple in the second sentence refers to the company?
Well, yeah, it's a good question. It's context, right? It's context clues.
Yeah.
If you're vague enough in your sentence, it might not be able to distinguish what you meant correctly, right? If you're too ambiguous in input, right? But in general, because you train the model to basically predict the distribution of human language, in this case, I mean, it becomes reasonable to assume that it will follow the distribution well enough so that, if you would assume that, maybe it would too. In reality, there's something I did want to touch on. Yeah, so thank you for bringing this up because basically, one of the analogies we drew about matmuls earlier in the talk was that it's sort of a matmul is sort of an array of vector similarities between the A and B, right? It's a dot product between the row and columns, and so there's this compression view of neural networks, and where you'll basically store bits of information and facts and meaning inside the weights. And in that way, you can retrieve the facts, like that the iPhone 17 was just released or something, through just a dot product, right? Because it's in there. You encoded that information there. And so this is, you might hear retrieval augmentation, but that's like a more direct approach. And in some way, supervised denoising sort of encodes facts in the way of shoving them in the weights, and then you can use it by doing a dot product. I wanted to highlight this average experiment we did earlier. Yeah, where we sort of built a average vector for each digit, and then just assigned a new, if we had a new input, we assigned the class based on which one it was closest to. And I wanted to basically explore the possibility that the last layer of any neural network kind of does this. So there's the size of n number of classes each time, some dimension d. And so it basically has to build some representative vector for each class, and then you're going to do a dot product on it, which means it needs to be the most, if the answer is going to be right, it has to be most similar to the label vector. And so I wanted to basically explore this idea that in some interpretable way, it's not perfect, but there's some analogy where every last layer of the neural network kind of does this. And everything else is like feature engineering, right? It's like augmenting and projecting and combining features of your input in ways that are advantageous to make them more separable. So maybe when you start, the vectors for 1 and 2 are quite close, but if your network is deeper and you have more layers to do your learned map moles, maybe it actually expands them, right? So your 1 and 2 get farther apart, nearly orthogonal. And then by the time it's time to do your final map mole, get your answers, it's much easier to distinguish them via this approach. And I think that's sort of what happens. Of course, it's not perfect because it's sort of because the network is trained as a whole, it's a landscape of this. It's all doing everything. But, I'd like to just plant that in our heads. I think it's useful. So thanks for bringing that up. But yeah, I think they can retrieve facts and they build concepts in vector space. So context, right? Anything else? We just got into Q&A here. Yeah. Well, there's nothing there on Zoom. I guess we get a break for lunch. If you think of other questions when when you're on lunch, let's ask them when we get back. But my idea was, so I don't know where they're doing. They said they're doing lunch for the.
It's at the first floor over there.
So obviously, you're AP Bio resident, then go eat lunch. But I wasn't able to get an answer about if other people were like allowed to do that. So like, I don't know. I think I'll probably serve you lunch, but I'm not telling you to go get lunch. So that's all I'm saying. So, but yeah, we'll meet back here at let's say 12:30. To do our notebooks. Sorry, you just shut up.
Yeah.
But yeah, that sound good? Sweet. I'm going to turn off the meeting. I don't have this unnecessary recording, but I'll turn it back on. So I will see all you guys there too. Bye bye.